let me just do the honor. So let me welcome everybody to this series of seminars. So this is a joint seminar now okay, not now, but since a couple of months ago, of probability and stochastics analysis of Técnico in Lisbon, and also organized by Brazil and Argentina, and in Brazil, several universities and several universities in Argentina as well are organizing this. So today we have a speaker, Tal Orenshtein. I hope to have said it correctly. Yeah, okay, good. So Tal, you are a postdoctoral researcher at the Technical University in Berlin, in the group of Jean-Dominique Dolchel. I hope I said it correctly. And so let me just give some quick words about you, Tal. So you finished your bachelor in mathematics in the University in Jerusalem in 2007. And then you did a master and a PhD at the Weizmann Institute of Science under the supervision of Gady Kozma, correct? Yeah? Good. So I have to tell you, so you have, it's a pleasure to have you here, and it's a pity that it's not in person. I do hope that we can do this seminar next year in person in Technical. So my invitation is open. Whenever you want to come, just let me know. And today your talk will be about rough walks in random environments. Please go ahead, and thank you so much for accepting this invitation.
Thank you, Patricia, and thank you for everybody for being here. Yes, so I'm going to. So the title of the talk is "Rough Walks in Random Environments," and this is due to an application of a thing that I want to tell you about. So the plan of the talk is to tell you a little bit about rough path. Then explain our program to consider homogenization on rough path, and give some models, particular models like regenerative processes and Kipnis-Varadhan additive functionals of Markov processes theory, and some applications to random walks in random environments and the random conductance model in particular. And please don't hesitate to just stop me if you have any question during the talk. And I assume that not all people here are familiar with rough path, so I'm going to give you, let's say, 3 slides of a crash course on rough path, okay? And if you are familiar, then excuse me for being very loose. But let's see. So the point of view that, so rough path is dealing with the following problem. So we're all familiar with the universality of Brownian motion, right? So Donskoy's invariance principle is telling you that if you have a random walk, which is the sum of IID random variables with mean 0 and variance 1, and you take your random walk X and you diffusively rescale it by speeding up time by n squared and by dividing by n, yeah, and taking a Cadillac version, or taking X tilde to be the linear interpolation to create a continuous path, then both are going to converge to a standard Brownian motion weakly in the Skorocha topology, no matter what is the distribution of the jumps, right? So Brownian motion is universal. So maybe we can take it to the next step, considering stochastic differential equations. So the point here is as follows. Let's assume that you have a stochastic differential equation here written in an integral form for a nice f, okay? And you want to consider this as a stochastic integral, so Ito integral. And now we want to approximate this equation by approximating the Brownian motion. So we approximate the noise by taking our Cadillac process here by taking just differences. So to create a difference equation, and you can show Wong and Zakai in 65 show that this converges weakly to the solution of your stochastic differential equation. So this is a good approximation. This is very natural. However, if you take the second approximation, so this X tilde that we had, linear interpolations, then this is absolutely continuous. So you could try to solve this with respect to a Riemann-Stieltjes integration, right? And then this will converge weakly to a solution to a stochastic differential equation as well, but it's going to be a different stochastic differential equation. So this is the Ito part, but you're going to have to pay a price of a drift. And this is nothing else but the Stratonovich integral. Okay, so yeah, so this is well known. For the difference between Ito and Stratonovich and approximation. But what does it tell us? It tells us that that we have somehow an incomplete information when we just know that something approximates a Brownian motion. In other words, the Ito map, taking the driver of the differential equation to the solution, is not continuous in the Skorochod topology. However, notice that this is the two things that I mentioned here. They are not relevant. So the law of the process is not relevant. So we do have a universality somehow. We just need to extend the notion. We just need to include the notion of integration in the universal object that we are after. This leads us to a definition of a rough path, Reliance in 98. So if you fix P between 2 and 3, a P variation rough path is a pair, okay, defined by pairs of times S smaller than T in a compact interval, so that the first level, this is the name, the first level is in RD, and the second level is a D by D real matrix, so that the first level, you should think about it as a path, and there is a connection between the second and the first level that is given by the so-called chance relation, which tells you that if you take S smaller than U smaller than T, you should see this this object here. So this is somehow a generalized increment. If it was an increment, it was 0, but you have here to take this product of the first level. And the second condition is an analytic condition that provides you the topology. And what you want is that the first level has a finite P variation norm, and the second level has a finite P over 2 variation norm. And if you recall the definition of a P variation norm, then this is given by increments, right? So there is absolutely no problem to just define to extend the definition to also to this type of path. Okay, so this is a definition of a rough path, and it defines also a topology, right? And Terry Lyons and Massimiliano Gubinelli proved that if you now have a rough path, calligraphic Z here, in this pair, then you can construct the rough integral. So you can construct an integral with respect to this path for a large class of y's. Okay, so that the map taking y and z to the integral is going to be continuous in a suitable space. I don't want to specify the topology because it's not relevant for the message. And moreover, the Ito-Lyons map, now taking the driver, the rough path, to the solution of this rough differential equation now, is continuous in a suitable topology. And what it tells you is that if you now have a sequence of drivers converging to a certain driver, then the solutions to the stochastic differential equation, to the rough differential equation now, is going to converge as well. Okay, so the point is that now, if going back to what I mentioned, the point is that the notion of integration is encoded already in the definition of the approximation. Okay, that was a crash course on rough path here. And let me now tell you what we are interested to do with this. So the idea that we're after is to take random processes, stochastic processes, that have homogenization, okay, that satisfy the functional CLT, and we would like to lift them to the rough path space and to prove functional CLT in the rough path topology. Okay, and from the point of view of SDE, this can give us non-trivial examples of noise approximations. Okay, the noise is the Brownian motion. And from the point of view of models, specific models that satisfy homogenization, this gives you a richer picture of the model on large scales. And what I'm going to show you today is that this is done for regenerative processes and for additive functional with Markov processes. These are two extreme large classes. And each of these can be applied to random walks in random environments for different type of classes. Okay, and last thing about rough path, and maybe if you're not familiar with that and you're completely not interested in all of that, this is something that I think it is important to know. So let's assume that we have a sequence of semi-martingales, okay, or martingales if you wish, and so that we take their Stratonovich lift, okay, iterated integral with respect to the Stratonovich integral, and they converge in the rough path topology to a Brownian motion in the first level. And the second level is a Stratonovich iterated integral of the Brownian motion, plus some linear perturbation. So there is a D by D matrix gamma, and this is the structure of the second level. So let's assume that you know that. Okay, you don't know anything about rough path, you just know this fact. And you now take an approximation of an SDE, okay, with respect to this Zn. And here is a Stratonovich integral. Then a theorem by Kelly is telling you that the Stratonovich SDE is going to converge to a Stratonovich SDE with a certain correction in the drift. What is nice is that this correction can be computed explicitly in terms of this gamma. So you see, so if you wouldn't know the second part, you might think that this should be your limit. But if you know something about the second level, it tells you, you know, how to correct your prediction. So let me give you an easy example, just to have something in mind, and this is going to be in the spirit of what I'm going to show you. So let's construct two processes, discrete time processes on Z2 coupled together, and we'll do it like that. So in the first 4 steps, the two walks, the one on the left and the one on the right, are going to go together and perform simple symmetric random walk, let's say something like that. So both of them are doing together this, okay? Then the left guy is going to do a deterministic loop, okay, clockwise, starting from up. And at the same time, the other guy on the right is going to stay in its position for 4 steps. And then after 4 steps, we're going to iterate the whole thing. So the left guy is going to continue with, so both of them are going to continue for 4 steps with simple symmetric random walk. And then the left guy is going to do a deterministic loop starting from up, and the other guy is going to stay in its position. Now you can convince yourself that if we call the left guy X, the other guy Xn, X bar, and we diffusively rescale them, then take linear interpolation, say, both of them are going to converge weakly to the same Brownian motion. Okay. In other words, you don't see these loops in the limit. Okay. However, you can compute, and if you are going to take the Strotonovich iterated integral of the right guy, then you're going to see that it will converge to the Strotonovich iterated integral of the Brownian motion. So this is just going to be 0. While the other guy will have a certain correction here. So we're going to see a 2x2 antisymmetric matrix here, non-trivial. Okay, so some C non-zero. I think it's pi over 2 or something like that. Okay, so in other words, this correction here captures these loops that you cannot see from in the first level. Okay, let's generalize this concept, and we present regenerative processes. So, by the way, questions so far? No. Okay. Yeah. So, a regenerative process is a discrete time process on RD, so that its increments form a delayed renewal process. What do I mean by that? I mean that you have an infinite sequence of random times, so that you can look at your walk and you can cut it to pieces between these times, okay? So that these pieces, jointly with the size of these pieces, these are called regeneration times, okay? So and regeneration intervals. So the pieces of your walk jointly with the regeneration interval, these are going to be IID, maybe except for the first piece that is going to be independent. And this is just to have some generality. Okay. So examples, the simplest example is a random walk. So your pieces are going to be of size 1, right? So this is just 1. And then these guys are just going to contain one element, the jumps. So this is going to be IID. Another example, actually 2 examples, is what I just showed before. So every 8 steps, the path is going to be IID. So these pieces are going to be IID, right? The two examples. And if you want to have other example that these guys are random, so the regeneration times are random, what you can do is you can say a positive recurrent Markov chain, YK, say on finite state space. And you can take a nice function or a function on that state space, and you can just take an additive function. So you can sum up f evaluated on the process in time. Right, so and then if you just wait until you hit for the kth time a certain state, then this is going to create a regeneration structure. Okay. And if you're not if this state is not the initial state, then this is actually indeed a delayed renewal process, right? Okay, and I'll mention other more complicated examples. This is just something to have in mind. And now to define some regularity condition here, and we call it the second moment condition. So regenerative process has the second moment condition if the deviation of the process norm square on a piece times the size of the regeneration time interval has finite expectation. And why this is a second moment? Well, it generalizes the second moment for random walk jumps, right? So in the case of random walk, as we said, that these sizes are just 1, and these are just the jumps. So it contains one element. So this is just the second moment of the jump. Okay, it is nothing but a generalization of that. And let's now discuss the first theorem in this direction. So yeah, we would like to take a function. We would like to prove a functional CLT for this guy. So let's take a regenerative process X to satisfy the second moment condition, and let's assume that it is centered on the regeneration times. Okay, and now we diffusively rescale it and take linear interpolation like that, and then take the Stratonovich lift. Okay, so then a theorem together with Olga Lopuzansky and also a follow-up on a follow-up paper by myself is as follows. So for every p between 2 and 3, we have a reconvergence in the p-variation rough path topology to a rough path that has in the first level a Brownian motion. And in the second level, we have a Stratonovich iterated integral of this Brownian motion plus a linear correction. And moreover, this linear correction is called the area anomaly, and it has the following form. It's the expected antisymmetric part of this iterated integral on a regeneration interval divided by the expected size of the interval. Okay, and remember that this is the d by d. This is a d by d matrix. This guy here. So this is just to make sure that you're with me. This is the I jth coordinate, and this is the I jth coordinate of this guy here. Okay. Some remarks. First, this second moment condition is optimal, and the counterexample is a random walk, right? This is just the second moment condition for the random walk, which is necessary for functional CLT. And yeah, so this is related to the theorem by Kelly, that now we can compute if we want to approximate an SDE by a regenerative process, we can compute the correction that we need. And the last remark is that you can give a geometric interpretation to this object, and it is indeed in area. So let me give you a sketch, but this is by no means related to reality, because our processes are assumed to be centered, and what I'm drawing now is not centered, but I think it is okay anyway to understand what I'm talking about. So if this is xi, the xi coordinate, and this is the xj coordinate, the ij plane, and our process is a regenerative process, so let's assume that we have these times, okay, something like that. This is a progress in time. Then to compute gamma, what you need to do is you need to draw a line in the time arrow between x tau 1 and x tau 2, and then you compute the area above this line. Okay, so the signed area. So if this is a plus and this is a minus, so the signed area, let's call it area. So gamma ij is going to be the expected area divided by the expected size of the interval. Okay. So tau 2 minus tau 1. Okay, so it is an actual area, and this is why it is called the area anomaly, and you can actually compute it. Okay, questions so far? Okay. Okay. So some applications I just want to mention. Don't have time to explain. Ballistic random walks in random environment in dimension larger equal than 2, and if you are familiar with that, these are the conditions that I'm referring to. If not, this is not going to tell you anything anyway. But ballistic random walks in random environments under the annealed law, they form a regenerative structure. This is a result by Snitman and Cerner. And Snitman also proved that all moments of this regeneration intervals are finite. In particular, you can apply a theorem and you can compute the area, the correction. If you want an example that you don't have all moments, you can get it from random walks in Dirichlet environments, dimension larger or equal than 2. There is some trapping parameter that kappa, so that you have exactly k minus moments for the regeneration intervals if kappa is larger than 3. Okay, so you can get these type of examples. And you can also take random walk in a fixed periodic environment, something which is periodic on boxes. And this is very easily shown to satisfy a regenerative structure that you can create plenty of examples that you can actually compute and show examples for gamma, which is non-zero, whatever you want essentially. Okay. That was the first part of the talk. So I try to convince you that the whole thing is essentially easy and natural, right? So these processes are IID-like, so they should, if you rescale them, then you should get a functional CLT. And the message is that, there is also a local effect that you cannot see in the usual first level classical standard functional CLT, but there is the area in these small intervals, averages, and you can actually compute it. However, most of processes that have functional CLT, or let's say many processes that have functional CLT, they don't have this IID-like structure. Unfortunately, fortunately or unfortunately, a large class of processes, such processes are additive functional of Markov processes. Okay, so we saw an additive function of a Markov chain, right? That was positive recurrent, but apparently you don't need positive recurrence in order to prove functional CLT, and this relates to the Kipnis-Varadhan theory. Now, I know that there are experts in the audience, and in particular, our work is based on the book. Okay, then the book is the book by Komorowski, Landim, and Ola, and this is a very good reference for the things that I'm going to tell you now. But if there are people who are not familiar with that, then I hope that I can explain and clarify things for them. And this is the idea. So what we would like to do. So on this part, first, we are going to work on continuous time processes, Markov processes. And this is easier to work with. Let's see what do we want. So we have a stationary and ergodic Markov process, ext. Okay, stationary with respect to the distribution mu. L is the generator, and we have a certain function from the state space to R, which is measurable and bounded, and has expectation 0 with respect to mu. And let's go already down, and I will tell you what do we want to do. We want to prove a functional CLT for the additive functional. What is the additive functional here? It's the time integral of f evaluated on the process. Okay, so we speed up time by n squared, and we divide by n. We want to prove that this converges to a Brownian motion. So how to do that? So the first step is to try to solve the Poisson equation. So you want to find some phi in L2 so that you have a solution to this equation that satisfies this relation. And if you find such a phi in L2, then you can define the so-called Dynkin-Martingale like that. So this is going to define the martingale. Okay, so you evaluate your phi at the end point, at the end time, on the process at the end time minus the process on the initial time, minus the time integral of the generator acting on phi evaluated at the process. And this martingale is very nice because you can compute its predictable quadratic variation. So let's do that by already diffusively rescaling it, speeding up time by n squared and divided by n. And you can check and see that this is going to be the predictable quadratic variation. It's this time integral. And what is nice is that you notice that this, you see an n square here and an n square here, and here is a function of your process, which is stationary and ergodic. Therefore, you can apply the ergodic theorem to get this limit in L1 and almost surely, of course, assuming that this is finite. We have a lot of assumptions, right? Phi squared is in the domain of the generator, but I'm trying to deliver the idea of the proof. Okay, so the ergodic theorem is telling you that this converges to that. So you have a control on the quadratic variation. You have a martingale, so you can apply the functional CLT to get a Brownian motion. And now, going back to the Dynkin's martingale, let me move the equality here and this guy here. Okay, I did nothing. Then you see the integral of f is the integral of minus L phi, which is just the sum of these two. Okay, so rescaling is essentially doing a rescaling of the martingale plus the rescaling of this error term. But this error term, well, by stationarity, this has the same law. But anyway, it is bounded, so it is going to zero in probability. And so the functional CLT for the martingale is the functional CLT for the Brownian motion. Okay, so this is the idea. Okay, and now sometimes, well, in most of the cases, you actually don't have a solution to the Poisson equation. And then what you can do is you can solve the resolvent equation. So you take a lambda, which is positive, and you solve this equation instead. And this always a solution in L1 actually, because this is you can write explicitly the solution as a green function with a killing of rate lambda essentially. Okay, and to say that you have a solution to the Poisson equation is to say that when lambda goes to 0, this converges in L2, right? And here we arrive to the so-called Kipnis-Varadhan theory or theorem, and this tells you that in fact you can allow the L2 norm of phi lambda explode. It doesn't have to go to something. But the condition that you need in order to achieve a functional CLT is sometimes called the H-1 condition. It has different formulations. Here is the formulation for this talk. What you need is that your L2 norm of phi lambda is going to infinity slower, sympathetically slower than 1 over square root of lambda. okay, as written here. And you need another condition that phi lambda L2 product with minus L phi of lambda is a Cauchy sequence, exactly what is written. And if you have these two conditions, well, then the way the proof works is that you go back to what we did with the Poisson equation, and well, you don't have exactly this. You have a certain correction that you need to take into account, and then you do smart things in order to use just these two conditions and to get your functional CLT. And one point that I want to mention is that these two conditions, they're always hold if X is reversible. Go to the book for reference. And in fact, the original Kipnis-Varadhan theorem assumes that X is reversible. Okay, and use that. Later on, people understood that all you need is just these two conditions and other conditions as well. Okay, that was a brief discussion about the classical Kipnis-Varadhan. And now we arrive to a rough version of the Kipnis-Varadhan theorem. Okay, so this is a joint work with Jean-Dominique Teuchel and Nicolas Tarkovsky. And here, let's take a Markov process, and we start from a stationary ergodic distribution, which is also stationary ergodic for L star. Okay. And let's assume that we have a function f from the state space to Rd, which is in L2, so that it has expectation 0 in all coordinates. Yeah? And let's assume the h-1 condition as I defined it. And let's take the additive functional of this Markov process already rescaled. Then, if we take the Stratonovich lift, okay, this is absolutely continuous. So the Riemann Stieltjes integral. Then it converges weakly in the rough path topology for every p between 2 and 3 to a rough path that has in the first level the Brownian motion. That's the classical Brownian motion from the Kipnis-Varadhan theorem. And in the second level, it has a Stratonovich iterated integral of this Brownian motion plus a linear correction. Okay, and this Brownian motion is, so this is well known, and the quadratic variation here is given like that. So it's twice, so the quadratic variation at time t is twice t, the limit as lambda goes to 0 of the expectation of phi lambda tensor with minus the symmetric part of the generator acting on phi lambda. And we have a description of our gamma, or of our linear correction, the area anomaly here. And this is the same limit, the same type of, it looks the same, only that instead of minus the symmetric part of the generator, you take the anti-symmetric part of the generator. So if you wish, this is the anti-symmetric missing part of Kipnis-Varadhan, maybe. Okay, and in particular, if L equals L star, then this is 0 and you don't see a correction. So the correction is coming from anti-symmetry. Again, also here. Okay. Questions? Okay, I hope that everything is clear and not the opposite, but okay, we'll see. I don't. Yeah, you see, I have 15 more slides. I don't have a lot of time, I guess. So yeah, I want to say something about the proof, but I'm not going to tell you everything about the proof. So I just want you to realize where the correction is coming from. I think that this might be interesting. So let's assume again that we have a solution to the Poisson equation. Okay, I think this is enough to for understanding where the correction is coming from. And then we saw that we can write our process, our additive function on this scale, as a Dynkin martingale plus this plus this arrow term, right? And now let's take the iterated integral of z with respect to itself, with respect to Riemann-Stieltjes integration. Okay. Then I'm keeping the dz here. So this is absolutely continuous. So this is again dz. And I'm writing this guy plus this guy. Okay, this is the m plus the l. Okay. And now the first term, the ergodic theorem, is telling you that you see that you have an n square here. If you do a change of variable in the integration, you get the 1 over n squared outside, and you speed up time by n squared. So this is just going to converge to the expectation of what's written here with respect to mu, right? And well, it's 0, just 0, and right, because this is the expectation of this guy. And for the other guy, for this guy, well, f, remember f is L of phi, and is minus L of phi, and we have another minus, so in total we have a plus. So this is the expectation and the limit. And remember that because this is where the correction is coming from. You will see it in a second. So let's now deal with this guy, this part. So first, z is a finite variation. So if we do integration by part, we don't pay the covariation there. So moving, so the integral of m dz, the Ito integral, is just the product of the endpoints minus the integral of z dm, and I'm writing it like that because it's transposed. Okay, so I thought that this is the best way to write it down. And then what is nice is that there is an available theorem by Kurz and Porter from 91 that tells you that if you can control the quadratic variation of the martingale that you take a stochastic integration with respect to, then you have a limit to these approximations. Okay, and moreover, well, you need to control these two jointly, but you can. So what you have is that Zn, Mn, and this integral, they all converge jointly. These guys, they converge to the same object as we saw, and this guy converges to the iterated integral of the Brownian motion in an Ito sense. Okay. And okay, now we just add this guy. So our integral of m with respect to z is converging to the tensor of the Brownian motion minus this integral of b with respect to itself transposed. Okay, good. So overall, if we add the first term that we know that it converges, what we have is that this converges to these three terms. And yeah, now doing integration by parts for this guy here, right? So move this guy here and this guy here. You see that you get this equality here, just integration by parts. And now we have a formula for the quadratic variation of B, right? You remember this is from Kipnis-Varadhan. So we use 1/2 of this to get the Stratonovich integral, and the other 1/2 is exactly what's written here. So it's a minus the symmetric part of the generator and plus this object. You see, and now what we have is just L minus the symmetric part of L, which gives you the anti-symmetric part. So in particular, if L was self-adjoint, then you would have here LS, right? Because L equals LS, and then this would be C, would cancel. Okay. Yeah. Yeah. The next point is tightness, but we needed to prove some new estimate, but I will allow me to skip that. Okay. So this is rough Kipnis-Varadhan, rough version of the Kipnis-Varadhan theorem, and this is a standard application is to the random conductance model. So first, what is the random conductance model? Yeah, so we are on ZD, okay, and on every edge, so here we are on Z2. On every edge, nearest neighbor edge, XY, you put weights, omega XY, which are non-zero, which are positive. And a configuration of such weights, also called conductances, is called an environment of conductances. Okay. And given an environment omega of conductances, you can define a Markov chain X omega on ZD in a natural way, right? In a natural way. So you define XT by saying that it jumps from X to Y with rate omega X. Okay. And in order to prove functional CLTs for that, first, what you want to do, given an environment omega, what you can do is you can write your process as the process minus the drift plus the drift, right? This is always what you can do, and you call this this is a martingale, and then you have your drift. Now, what is the drift? The drift is something that you can integrate in time locally. And what is nice about that is that you can define this drift at time t as a time integral of a function acting on a different Markov process. And that Markov process is going to be the environment seen from the walker. So rather than moving the walker on ZD, so whenever it jumps along an edge, what you can do is you can shift the environment in the opposite direction so that the walker is always on the origin. And if you do that, you create a Markov process on the space of environments now that is called that is the environment seen from the walker. And now this is for one fixed omega. Yeah, sorry, I didn't specify what f is. So, and then given an omega, this is your location. In order to know what is your local drift, you just need to look at the origin, and then you create this. Then you can compute your local drift where you are. Okay, and then you take an integral along that. And as I mentioned, this is a Markov process. And now it turns out that if you start your environment from an IID conductances, then this Markov process is going to be ergodic and reversible with respect to this IID measure. So you create a martingale plus an additive function. Okay, and now what you can do in order to achieve so this is what you do in the standard way. So you somehow prove that each of these converge to a Brownian motion. And what you need is to understand how they converge together, right? Because they are not independent or anything. And in order to prove a rough invariance principle for this model now, notice that what you need to do is you need to take your martingale part. When you lift it in an Ito sense, it will converge to a Brownian motion and the iterated integral of a Brownian motion in the Ito sense. And the additive functional part is going to converge to a Brownian motion and an iterated integral of a Brownian motion in a Stratonovich sense. And here, this is due to the rough version of Kipnis-Varadhan. And since this process is reversible, this is just going to be zero. So the gamma is going to be zero. So you have no correction. So now you have an hybrid between Ito and Stratonovich, and you also need to deal with the integral of m with respect to z and the integral of z with respect to m. Okay, you do that. And what we managed to prove with in the same paper with Jean-Dominique and Nicolas is that if your conductances are independent but stationary, okay, and uniformly elliptic, this is what I mean, then you have an annealed convergence weakly in a rough path topology. Again, the same formulation to a Brownian motion. And in the first level, and in the second level, you see a Stratonovich iterated integral plus a linear correction that you can write explicitly as minus the weights on diagonal matrix, which has minus the weights of the conductances in all directions. Okay, and so this is some kind of a hybrid between the two. And I want to mention that if you take the Stratonovich lift and not the Ito lift, then you don't have this correction. Okay. Yeah, now I really don't have a lot of time, so I just want to just allow me to take 2 minutes, and just to mention another result, another type of result on random conductance. So additive functions of Markov processes are very useful because you can apply them to non-reversible processes as well. However, for the random conductance model, they give you just an annealed result. Okay, so if you take expectation with respect to the environment, only so with respect to the measure on the environment, you have a convergence in expectation to a Brownian motion. However, people are very much interested also in quench results. Quench results are so that you sample an environment with respect to the initial measure on the environments, for example, this IID measure, and you want to prove that for almost every environment omega, you have a functional CLT with a Brownian motion which is independent on the environment. This is a quench result, it's much stronger. In order to prove that, you need something more sophisticated that unfortunately I will skip. And I will tell you that in a work in progress that we have now with Johannes Bäumler and Noam Berger and Martin Slovic, we did that. We took the perspective of that people do to get this quench result, and we managed to get the quench result in the conditions that you have a recent result by Paul Dario that gives you moments of the corrector coordinates, if it tells you anything. And in these settings, so here are the settings, we can prove a quench result in the rough path topology and get also a different identification of the correction. Okay, sorry about the fuzzy ending. Yeah, I will also skip the summary, and Yes, and this is the list of contributions that I mentioned. So these three you can already find, and this guy in the future, in the near future. And that was everything I wanted to say. Thank you.
Thank you. Thank you so much, Tal. So let's thank Tal for the very nice talk. So Tal, it was very nice, very pedagogical. Okay, I lost you in Zoom. Ah, yes, you're here. So is there any question from the audience? No? Okay. So
I might have some questions.
Yeah,
so,
Claudio, go ahead.
Thank you very much for this very nice talk. So, well, there are natural questions on. So one of them, it's this Kipnis-Varadhan relies very much that you're starting from a stationary state. So do you have any idea how to deal if you start from a non-stationary situation? And then Kipnis-Varadhan has been well applied in many different contexts. So for instance, in attacked particle, in interacting particle systems, and you have also these, well, these conditions which you mentioned, H-1, so you have a graded sector condition, which is enough to, in order to prove these type of bounds, you need to prove Kipnis-Varadhan. Do you have anything similar in your theory?
Okay, so unfortunately, my answer is going to be quite short. These are very good questions, and these are things that I would like to check. And also, I invite other people that are interested to go in these directions. For the non-stationary case, I have no idea. I have no idea how to deal with that. And I would expect to essentially to be able to prove similar results for other, for example, for the graded sector condition, also in the rough path sense. Yeah, so this is in the future, and this is absolutely a legitimate question to ask.
Thank you, Tal.
Yes.
So any other question? No? So let's thank Tal again for the very nice talk. Hope next time in person, Tal.
Yes.
Let's hope that, let's cross fingers that next time we'll do it here in technical. Claudio, then you have to come to technical. Yeah, let's try to do it. Okay, very good. So so next week we continue at the same time. I don't remember who is the speaker, Claudio, help me. Do you remember? But we have it on our webpage in any case. Oops.
Is Genesphere?
Genesphere, yeah.
Okay, perfect. Hi, Pablo.
Hello.
Hello, how are you?
Nice.
Fine.
Nice to see you after some.
After some time. Yeah,
Yeah.
good.